Greetings! Our group will have a quick discussion about the electronic structure of atoms in order to better understand and know the concept of this topic. A total of 4 quantum numbers are used to describe completely the movement and trajectories of each electron within an atom. The combination of all quantum numbers of all electrons in an atom is described by a wave function that complies with the Schrödinger equation. Each electron in an atom has a unique set of quantum numbers. According to the Pauli exclusion principle, no two electrons can share the same combination of 4 quantum numbers. Quantum numbers are important because they can be used to determine the electron configuration of an atom and the probable location of the atom's electrons. Quantum numbers are also used to understand another characteristic of atoms such as ionization energy and the atomic radius. In atoms, there are a total of 4 quantum numbers: the principal quantum number, the orbital angular momentum quantum number, the magnetic quantum number, and the electron spin quantum number. The principal quantum number describes the energy of an electron and the most probable distance of the electron from the nucleus. In other words, it refers to the size of the orbital and the energy level of an electron is placed in. The number of subshells describe the shapes of the orbital. It can also be used to determine the number of angular nodes. The magnetic quantum number describes the energy levels in a subshell and refers to spin electron, which can either be up or down. Further explanation of these 4 quantum numbers, here is Mr. Jerome Gabionza.
The principal quantum number, n, designates the principal electron shell, because n describes the most probable distance of the electrons from the nucleus. The larger the number n is, the farther the electron is from the nucleus, the larger the size of the orbital, and the larger the atom is. N can be any positive integer starting at 1, as n is equals to 1 designates the first principal shell. The first principal shell is also called the ground state, or lowest energy state. This explains why n cannot be 0 or any negative integer, because there exist no atoms with 0 or a negative amount of energy levels or principal shells. When an electron is in an excited state or it gains energy, it may jump to the second principal shell, where n is equals to 2. This is called absorption, because the electron is absorbing photons or energy. Known as emission, electrons can also emit energy as they can jump to lower principal shells, where n decreases by whole numbers. As the energy of the electron increases, so does the principal quantum number. Here are some example problems that can help you better understand the principal quantum number. For our question number 1, the answer is third principal shell. As we recall the lesson earlier, the value of n is equal to the number of principal shells. Then n is equals to 3 indicates the third principal. The orbital angular momentum quantum number L determines the shape of an orbital, and therefore the angular distribution. The number of angular nodes is equal to the value of the angular momentum quantum number L. Each value of L indicates a specific S, P, D, F subshell. The value of L is dependent on the principal quantum number n. Unlike n, the value of L can be 0. It can also be a positive integer, but it cannot be larger than the one less than the principal quantum number. Here is also an example problem that can help you better understand the orbital angular momentum quantum number. In this example, possible values of L are the ones we're finding if n is equals to 8. And since L can be 0 or a positive integer less than n minus 1, it can have a value of 0, 1, 2, 3, 4, 5, 6, or 7. The magnetic quantum number ml determines the number of orbitals and their orientation within a subshell. Consequently, Its value depends on the orbital angular momentum quantum number L. Given a certain L, ML is an interval ranging from negative L to positive L. So it can be 0, a negative integer, or a positive integer. I'll give you an example problem. So here is our problem. If n is equals to 3, then what are the possible values of L and ML? Well, the possible values of L start at 0 and they work their way all the way up to n minus 1. In this case, n is 3, and 3 minus 1 is 2. So our possible values of L are 0, 1, or 2. For the n is equals to 3 electron, there are 3 possible values of L, and again, the electron that we are talking about is only going to choose one at these 3 values of L. Okay, so let's bring m sub L into the mix. When we have an electron at n is equals to 3, and let's say it chooses L equals 2, if it chooses L is equals to 2, what are its options for the ML? Well, m sub L starts with 0 and it works its way all the way up to plus or minus L. And since we're starting from 0 to plus or minus L, the possible values of ML here are 5 only, namely 0, positive 1, negative 1, positive 2, and negative 2. The number of possible values just tells us the number of possible directions for the orbital. So, if the electron chooses 0 as the value of L, there is only one possible direction or one value of ML. If the electron chooses 1 as the value of L, there are only 3 possible directions or 3 values of ML, and if the electron chooses 2 as the value of L, there are only 5 possible directions or 5 values of ML. Unlike N, L, and ML, the electron spin quantum number Ms does not depend on another quantum number. It designates the direction of the electron spin and may have a spin of positive 1/2, represented by an upper arrow, or negative 1/2, represented by a down arrow. This means that when Ms is positive, the electron has an upward spin, which can be referred as a sign up. When it is negative, the electron has a downward spin, so it is spin down. The significance of the electron spin quantum number is its determination of an atom's ability to generate a magnetic field or not. The fourth quantum number is dependent on the first 3, allowing the first 3 quantum numbers of 2 electrons to be the same. And as what we can see on our given values, the only thing we only need to find are the values of Ms, m sub s. Since the spin can be positive 1/2 or negative 1/2, here are the 2 combinations. N is equals to 3, L is equals to 1, ML is equals to 0, and MS is equals to positive 1/2, or N is equals to 3, L is equals to 1, ML is equals to 0, and MS is equals to negative 1/2. And there you have it. Those are the 4 quantum numbers used to describe completely the movement and trajectories of each electron within an atom. For our second subtopic, starting off with the first principle, here is Miss Tracy Cornelio.
For the next subtopic, we will discuss a short definition and how to write the electronic configuration under the Aufbau principle, Pauli's exclusion principle, and the Hund's rule. Starting off with the first principle. The Aufbau principle from the German Aufbauprinzip, also called the Aufbau rule, states that in the ground state of an atom or ion, electrons fill subshells of the lowest available energy. Then they fill subshells of higher energy. For example, the 1s subshell is filled before the 2s subshell is occupied. The order in which the orbitals are filled with electrons is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on. Here is a mnemonic diagram of the Aufbau principle. To write the electronic configuration using the Aufbau principle, we should first determine the atomic number. In the example, sulfur is 16, implying that it holds a total of 16 electrons. As per the Aufbau principle, 2 of these electrons are present in the 1s subshell. 8 of them are present in the 2s and 2p subshell, and the remaining are distributed into the 3s and 3p subshells. Therefore, the electron configuration of sulfur can be written as 1s2, 2s2, 2p6, 3s2, and 3p4. Another example is writing the electronic configuration of nitrogen. We determined that the element nitrogen has 7 electrons since its atomic number is 7. So, the electrons are filled into the 1s, 2s, and 2p orbitals. Note that s is equal to 2 and p is equals to 6. And since we follow the order in which the orbitals are filled, the pattern will be 1s, 2s, and 2p. But since 1s and 2s will be 4, and the nitrogen has only 7 electrons, the rest, which is the 2p, will only be 3. So the resulting electronic configuration of nitrogen can be written as 1s2, 2s2, and 2p3. For the second principle, here is Miss Jessica Hiccup.
The Pauli exclusion principle is the quantum mechanical principle which states that two or more identical fermions cannot occupy the same quantum state within a quantum system simultaneously. It is an assertion that no two electrons in an atom can be at the same time in the same state or configuration. We can take hydrogen, helium, and lithium as examples. For example, we can take a neutral helium atom as a common Pauli exclusion principle example. The atom has two bound electrons and they occupy the outermost shell with opposite spins. Here we will find that the two electrons are in the 1s subshell where n is equals to 1, L is equals to 0, and Ml is equals to 0. Their spin moments will also be different. One will be ms is equals to negative 1/2 and the other will be positive 1/2. If we draw a diagram, then the subshell of the helium atom will be represented with one up electron and one down electron. In essence, 1s subshell will consist of two electrons which have opposite spins. Similarly, if we have hydrogen, it will have 1s subshell with one up electron or 1s1. Lithium will have the helium core or 1s2 and then one more up electron or 2s2. What we are trying to depict here is that the electron configuration of the orbitals is written in this manner. In atomic physics, Hund's rules refers to a set of rules that German physicist Friedrich Hund formulated around 1927, which are used to determine the term symbol that corresponds to the ground state of the multi-electron atom. Hund's rule states that 1. Every orbital in a sub-level is singly occupied before any orbital is doubly occupied. And according to the first rule, electrons always enter an empty orbital before they pair up. Electrons are negatively charged and as a result, they repel each other. Electrons tend to minimize repulsion by occupying their own orbitals rather than sharing an orbital with another electron. Furthermore, quantum mechanical calculations have shown that the electrons in singly occupied orbitals are less effectively screened or shielded from the nucleus. Electron shielding is further discussed in the next section. Number 2. All of the electrons in singly occupied orbitals have the same spin to maximize total spin. For the second rule, unpaired electrons in singly occupied orbitals have the same spins. Technically speaking, the first electron in the sublevel could be either spin up or spin down. Once the spin of the first electron in the sublevel is chosen. However, the spins of all of the other electrons in that sublevel depend on that first spin. To avoid confusion, scientists typically draw the first electron and any other unpaired electron in an orbital as a spin up. Let us consider the correct electron configuration of the nitrogen Z is equals to 7 atom 1s2, 2s2, 2p3. The orbitals are half-filled. There are 3 electrons and 3 p orbitals. This is because the 3 electrons in the 2p subshell will fill all the empty orbitals first before pairing with the electrons in them. Keep in mind that the elemental nitrogen is found in nature typically as molecular nitrogen, or N2, which requires molecular orbitals instead of atomic orbitals as demonstrated above. Next, consider oxygen Z is equals to 8 atom. The element after nitrogen is the same period. Its electron configuration is 1s2, 2s2, 2p4. Oxygen has one more electron than nitrogen. As the orbitals are all half-filled, the new electron must pair up. Keep in mind that the elemental oxygen is found in nature typically as molecular oxygen, or O2, which has molecular orbitals instead of atomic orbitals as demonstrated above. To discuss and write the molecular diagram, here is Mr. Beson.
To represent the electronic configuration of atoms, orbital diagrams are used. But before that, we should know that there are 3 rules that dictate the way electrons are filled in atomic orbitals. First, the Aufbau principles rule, wherein electrons must completely fill the atomic orbitals of a given energy level before occupying an orbital associated with a higher energy level. Electrons occupy orbitals in the increasing order of orbital energy level. Second, Pauli's exclusion principle. It states that no 2 electrons can have equal values for all 4 quantum numbers. Consequently, each subshell of an orbital can accommodate a maximum of 2 electrons, and both these electrons must have opposite spins. And lastly, the Hand's rule of maximum multiplicity. It says that all the subshells in an orbital must be singly occupied before any subshell is doubly occupied. Furthermore, the spin of all the electrons in the singly occupied subshells must be the same in order to maximize the overall spin. Also, the rules for creating orbital diagrams as shown in the picture states that the lowest energy orbitals are filled first before the higher energy orbitals. The lowest energy starts from 1s, then 2s before reaching the 2p, and so on. Each of the orbitals gets 1 electron first, like the arrow pointing above, before a second electron is added to the orbital, like the arrow pointing downwards. Only 2 electrons of opposite spins can occupy each orbital, which means that inside a single orbital, there must be an electron facing up and facing down or simply in opposite directions. This is an example. What is the orbital diagram for sulfur? Let us look at the periodic table to see how many electrons sulfur has. In this case, sulfur has 16 electrons that need to be placed into orbitals. So here, we'll draw the atomic orbital for sulfur. And to do that, the first thing we have to write is the electron configuration. Sulfur has an atomic number of 16. That means it has 16 protons, and since sulfur is like all of the elements on the periodic table, they're neutral. So, we have 16 electrons for sulfur. Based on the discussion of Miss Tracy and Miss Jessica, we can identify the electron configuration of sulfur by the help of this table. So, the electron configuration of sulfur is 1s2, 2s2, 2p6, 3s2, and 3p4. We'll use this to write the orbital diagram. So, this atomic diagram here, all we're trying to do with this, or the electron configuration, is figure out where the electrons are. around the nucleus of the sulfur atom here. So, you can think of the nucleus being here at the bottom, and these are just energy levels surrounding the nucleus. Maybe think of it as shells. So, we'll start out. We have 1s2. We put our electrons there, opposite directions, like this. 2s2, and we've got 2p6. We spread them out first, and then we pair them up like this. 3s2, and then we end up with 3p4. Just like what we did on 2p6, we spread them out first, and then we pair them up like this. As you can see, we can also write this in a more horizontal manner, but it's the same thing. So again, all of these are just representations of where the electrons are, around the nucleus of sulfur atom. So that's it. That is how to draw an atomic diagram for an atom. In this example, we use sulfur atom. And here are the summary of our presentation. We hope you have gained an understanding of what electronic structure of atoms is all about. And that summarizes our presentation. Thank you.